Hey everybody, in this video we're going to talk about the sine rule. The sine rule is a rule that we can use with actually non-right triangles. So normally we reserve sine, cosine, and tangent for right-angled triangles. But with the sine rule we're going to use a little bit of a proof here in the beginning to show you how you can use this sine rule for non-right triangles. And then we also have a situation where we might have some ambiguous angles, some angles that we're not quite sure about, so we'll look at those also. So let's start with this first triangle, and we'll label this A, B, and C, the vertices here. And I'm going to drop the height down from B to side AC, and we'll call that point D. Now, what we're going to do is we're going to look at or try and find this height, because we can only use up to this point sine and cosine and tangent and all those other great things with that right triangle. So we're going to use the height here with our sine option. So we are going to well, first actually let's say we have to label our sides A, B, and C so we know what we're looking at. So right now we're going to focus on sine A, and that's going to be opposite over hypotenuse, so H over C. And then we're also going to look at sine C. So sine C is H over A, right? So we're looking at a different angle, but we're still going to that same height. Now, if we rearrange these a little bit, if we change our, with the sine A, if we multiply both sides by little side C, we can get that C sine A equals H. And we can do the same thing for the bottom and solve for H and get A sine C equals H. So now that we have two things that are equal in the same value, H, we can set those two things equal to each other. So we got C sine A, so that's the side C times the sine of angle A, equaling A, side A, times the sine of angle C. Alright, so if we divide the left side by C and we divide the right side by A, we get a proportion of sine A over A is equal to sine C over C. So we just found that just by setting up this height that we see that these two proportions are equal to each other. And if we were to drop that height, if we were to drop it from A to side A or C to side C instead of what we did, B to side B, we would also see that you could get the same proportion with B. So you get sine B over little side B. Sine big B over little side B. So this kind of comes out to show that even with a non-right triangle, because if we use the height in there, that we get this proportion that sine A over A equals sine B over B equals sine C over C. Or you could write it the other way with the values switched. As long as when you're using these proportions, you always have the signs in the numerator and the sides in the bottom, the denominator, or you have all of the sides in the numerator and all of the sine values in the denominator. You can't switch them. So you can't have like side A over sine B, sine A, and sine B over side B. Hopefully you can distinguish the differences. It's very similar sounding. But let's look at an example. Okay, so we're going to look at angle A is 32 degrees, side A is 3, side C is 5, and we're going to find the other angles for this. So let's start by drawing ourselves a triangle, and we got 32. Side A is opposite of that 32, so that's 3, and then side C, I'm just following the one from above, so we got 5 across from that. So that means this is going to be our angle that we're looking for, theta. So we set up our proportion. So 32, sine 32 goes with side 3, and sine theta goes with side 5. So we set up our proportion. And now we want to get sine theta alone because we want to find out what theta is. So we're going to multiply both sides of this by 5, and we get 5/3 sine 32 equals sine theta. I'm going to punch 5/3 sine 32 into my calculator, and I get 0.8832. And now I'm going to do the inverse of sine to find out what theta is of that same value. and I get approximately 62 degrees. Now this goes out a little bit further in the decimal, so I'm just rounding to keep it easy. So now we have theta equals 62 degrees, so if we wanted to find the other angle of this triangle, we would do 180 minus 32 plus 62, right? Add up the two that we have, subtract it from 180, and we get 86 degrees. Now here's a weird thing about using the sine rule, is I drew this triangle because it was one like I had up above, but I could just as well have made a triangle that looked like this, and where these two sides are the same. So I mean, that's still, that purple line, that's still a measurement of 3. So if that's still 3, then this is our theta, and now we've got a problem because this angle is clearly obtuse, where our first theta, the green theta, was acute. So we had looked at in previous videos that sine theta is equal to sine of 180 minus theta. So we know that this is the property of sine values. So if we take sine of 62, that's going to be equal to sine of 180 minus 62. Well, 180 minus 62 is 118 degrees. So this could just as well, finding all of this proportion, everything that we've done here, could just as well have been 118 degrees and not 62 degrees. So what we need to do is we need to check to see if this 118 also works with our triangle. So if we're looking at the purple sided triangle, then we get a value of 30 degrees. So based on the information in this example, we could have two possible angles two possible triangles for this situation. We could have one with one angle's 32 degrees, 62 degrees, and 86 degrees. And then we could also have one that is 32 degrees, 118 degrees, and 30 degrees. So this is that ambiguous case, those ambiguous angles. So you always, whenever you're using the sine rule and you've got one angle and two sides, you've got to check to see if you've got that ambiguous angle in there. So if there's another hidden triangle that you may not be considering. So let's look at another example. So we got a slightly different triangle just to kind of keep it interesting. We're going to still label them A, B, and C. And now we've got 55 for angle A, 4.5 for side A, and 3.6 for side B. So we're still going to try and find the other angles for this triangle. So we'll start with theta as being side B, since that's the opposite side of the side that we have, 3.6. We'll set up our proportions. So sine 55 goes with 4.5, sine theta goes with 3.6. Multiply 3.6 on both sides of the equation, and we get 3.6 over 4.5 equals sine 55. Punch that into our calculator to get sine of theta equaling approximately 6.5532. Again, that decimal goes on. I just rounded for easier access here. And again, our inverse of sine gives us 41 degrees for theta. So again, that's an approximate. There's some decimals in there I rounded just to kind of keep it nice whole numbers. So let's check to make sure to see if we have this ambiguous situation. So we take 180 minus 41, and that gives us a value of 139 degrees. So if we combine this with 55, we've got 139 plus 55, that is 194. So that's bigger than the sum of all the angles of a triangle, so this is not an option. So we only have one situation for this, and that is 55 degrees for our one angle and 41 degrees for theta, which leaves us with what, 96? So what is that, 86, 84? 84 degrees for our last one. Okay, so let's summarize this. When do we use the sine rule? Okay, so we've got two situations really is when we use this. So the first situation is if we have two sides and a non-included angle. All right, so what's a non-included angle? Well, that's like the two scenarios we just looked at, where we've got theta as one angle, and then we've got the opposite side and one of the adjacent sides. So that's two sides and a non-included angle. And with this, we always want to make sure that we check for ambiguous angles. Okay, always, always, always check that to make sure that you're not missing a triangle. The second option is if we have two angles and one side. So this is a little bit easier because if we have two angles in one side, let's say we know that these two and these two angles in the one side, well, we could easily find this last angle. So all we'd have to do is add up those two angles and subtract from 180, and we get that last angle. So there's nothing ambiguous here, right? So all the angles are going to be set forth for us right at the very beginning. So these are a little bit easier because you don't have to go that extra step to check like you do with the two sides and a non-included angle. But you know, these are basically the two different scenarios where you can use the sine rule when you're trying to find sides or angles of a non-right triangle. Now there is one other option, it's called the cosine rule, and we'll look at that in another video. So that's it for this time, and I'll talk to you soon.